The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
It's really our pleasure to be able to present to you guys today on behalf of all of us at 562 that have spent the last 6.5 years developing this code. What we're going to do now is kind of get in the meat and the guts of it, if you will, and this is the real practitioner's part of the code. What I want to do today is I want to kind of present, this is Chapter 6, and I want to present it in a format of a couple of worked examples, just so that you get the flavor of how we view you would need to use the code in order to successfully evaluate and develop a repair design. So that's what we're going to cover. I have 2 different examples for you. The first, an older building, really pretty beautiful building, hollow clay tiled roof, historic structure, built in the 30s. And along the way, new retrofit HVAC system. As you can kind of see from the overview of the structure, not a lot of room to put a new HVAC system, and they don't want to put it out on the ground, so we're going to use the attic space for this facility. Here's just and I know this is a little bit difficult to see, but here is the plan view of the attic space. That is a inverted T-beam construction, fairly common in the 30s. And I know this is difficult to see. I will provide you with a better section, but you see the inverted T in the attic space. And then numerically, from left to right, I just have the steel trusses labeled. And they look like that. So there's your truss, and the inverted T system frames right up to the truss, bears on it. The negative moment steel runs through the gusset plate of the truss. The area that we're going to be focused on for this particular example is right in the middle, which is really where it's going to see its maximum load. And so in cross section, 6 inches in width, 9.5 inches deep, and as Keith commented the other day, not too many 2.5-inch decks anymore, but a few still around. We have 2 5/8-inch diameter rods to carry the negative moment steel from truss to truss. And so the concern from the owner was they had some distress in the form of really fine cracking very near the end of the negative moment region. And so that began the preliminary evaluation, which is described in Chapter 4. And so we begin to look at it, and the loading here, if you look at trusses 4 and 5, has the maximum negative moment. And so from here, we can see that in Chapter 6, you're allowed to use historic default values. We put this in here so that you could, if you didn't need anything else, you could go back to the period of significance. In this case, we're looking at 1920 to 1949 for beams, 2,000 psi concrete. We provided that because we know that several historic structures, we don't have that information. We don't have construction documents. We certainly don't have test material. So a lot of times we don't need it if our structural repair satisfies our historic material properties. So we put that in there for use, and in here we're going to use it as a quick check, just to see where we're at. So here's our material property for steel, and you can see 1911 to 1959. We have grade 33. So we run the numbers, 2,000 psi concrete, 33 KSI steel. Our demand, negative 13 kip feet. I use a fee factor of 0.9 only because I don't know what my material properties are. That's specified both in Chapter 5 and in Chapter 6. So when I work that out, I'm good. So if I go back to my evaluation criteria listed in 6.1 of Chapter 6, the evaluation consists of two things. It consists of an assessment and or an analysis. You don't have to do both, but it provides for both as a complete evaluation. So here, I've satisfied my analysis, and I've taken care of my visual assessment, and for this structure I concluded that the cracking that was there, long-term cracking, likely shrinkage cracking, has probably been there for several years and the owner just noticed it recently. So my beam's okay. But I still have this issue of the new HVAC units, which I know you guys haven't forgot about. So we have to deal with those, and like most mechanical engineers, they want to put them in a place that hurts me the most. So there we are. So we see on 4 and 5, recalling earlier from our truss configuration, we're looking at that beam again, and now you can see I've really jumped up a negative moment on those two trusses, as you would expect. Right? So you know from my previous slide, back to my historical properties, as you might expect, I have an issue now. And so I'm way overstressed. I could just tell my mechanical guy to forget it, but because I'm a halfway diligent structural engineer, I'm going to have to deal with it. So the conclusion is I have to strengthen this beam. But if I'm a practitioner and I want a more refined analysis, the code allows me to go ahead and test the material properties. And if I test the material properties, I can go back to Chapter 5, and in Chapter 5, if the material properties are known, I can use a higher fee factor. So that's what I do. In Chapter 6, 643, here's the equivalent strength provision for concrete. Now, it's taken from ASTM 214, but it's a little different, and I want to point out to you this term, the coefficient of variation, is not the same term that you're used to previously, standard deviation. Okay? So don't call me later, run out and say, hey, this equation doesn't work, Chuck. But anyway, back to my design example, I do it. I come up with an equivalent compressive strength of 5,100 psi. And also, I'm required to get the exact measurements of the beam so that I know exactly what I'm working with in order to use the fee factor of 0.1 as permitted by Chapter 5. I do the same thing with my steel coupons. Again, you see I work through the math. And I have an equivalent. So now, based on that demand, with my 1.0 fee factor, I almost made it. And so you can see the benefit of, being able to go out, get the exact material properties if you don't have it and you need it, it may pay off. In this case, it didn't quite pay off, so I got to go back and strengthen the beam. So in the repair, I'm now going to use the material properties I've established, but I'm going to FRP strengthen it because, as we told you earlier, it's permitted in the code, and you follow the guidelines of 440.2R, walks you right through it. And now, my increased capacity, 37 kips, plenty good. Now what I should point out to you is there is a provision in Chapter 5. You need to go back to Chapter 5 And you need to make sure that you satisfy the provision for external strengthening, because that provision protects you to ensure that the structure remains intact in the event of impact damage or fire or some other event. So you need to go back and make sure you satisfy that criteria. But in general, what I've worked here for you has satisfied the code. And then again, note, I did not use 1.0 in my fee factor. That's only for evaluation. So when you go to repair, you're back to standard repair fee factor as designated in Chapter 5, and there you go. So, what did we get out of this one? The historic values often provide a quick check. Get you in the ballpark, let you know where you're at, and you evaluate the element with your standard fee factors. Evaluation on material testing is a bit more refined, and in most cases, that refined analysis, you may find that you have satisfied your demand. You get that reduced, that modified factor because you do have lower variability because your material properties are known. And then finally, we can repair it using 440R and the relevant standards in 318. So I have one more for you. This one's a little different. So this is a new structure now. Turner Roberts Recreational Center. The guys in the front row recognize it well. There are many issues with this structure. It was originally cast as a structural slab on carton forms. And the concern was that during construction, the carton forms collapsed. And so as you can see in the middle photograph, significant change in geometry of the beam and slabs. So the owner excavated out underneath it, exposed it, and so this begins the evaluation procedure. So a little bit of background for you. Relatively modern structure, 77 square feet. So it's sitting on reinforced concrete beams, drill piers, multi-use facility. And just kind of showing to you in plan, here's the multi-use rooms in the back, the indoor gymnasium in the front. This structure was evaluated by a whole lot of folks, and at the end of the day was determined that the gymnasium wasn't salvageable, but the multi-purpose area may be salvageable. Hairline cracks in the structures, I already discussed with you the construction errors, the carton forms. They did close it. Now the issue that we have here with this structure is the irregularity of the beams. I no longer, even though I have the construction documents, I no longer have with any certainty where the bars are placed, what my D is, how much dead load I have. So now I'm kind of limited by my analysis. But in my evaluation, I know one of the tools that I have in Chapter 6, if I go to 6.8, is I can load test it. Okay? So the load test is provided, as Larry alluded to, is provided by 437. It's referenced. 437 has a load testing standard. It's gone through the same consensus public comment process that 562 went through. So it's referenced in Chapter 6. Now 437 provides for two different methods, which I'm going to explain to you. We're going to focus on this part because, as I told you earlier, this part was demolished. You can faintly see that it's one-way slabs, pier and beam. Two procedures that 437 provides you. The first is monotonic, and this is going to be almost exactly similar to what's in 318 Chapter 20. Almost. Very, very similar. The procedure's the same. You load in 4-ankle increments. You hold for 24 hours. You measure the response, unload, and measure the final response. The acceptance criteria, evidence of failure, maximum and residual deflections. Now, I'll point out that in 437, the maximum and the residual deflections, you have to meet both. In 318, Chapter 20, you can either or. So slight difference in those two tests. Cyclic is another option. In cyclic load testing, there's not a 24-hour time period. You complete the steps. It's step-loaded, often using hydraulic loading in 5 equal steps, up, down, 2 steps, and then we go from 50 to 75 to 100. Generally takes about 2.5 hours. And the acceptance criteria is a little different, because now we're looking at behavior of the element. So we're looking at evidence of failure and the acceptance criteria of deviation from linearity. So we want to stay in the elastic range, and permanency ratio, both of which are well defined in 437. So for this case, we decided, because we didn't have really a way to pull down or anything to react above, we decided to test monotonically. So we determined our test load magnitude, and this is the test load magnitude in accordance with 437, which is a little bit different than Chapter 20 of 318, because the dead load of the structure is known. It's visible to you. You can go measure it. You can see it. We got a good approximation of the dead load. So we know what that is. We developed the superimposed load, and our test load magnitude is, there you see it, 166 PSF. This is our test region. We chose this so that we can take the representative areas. You see here we have the larger spans, both for the beams and for the slab, and the owner's concern that the piers may not have been well founded. So we do that. We censor our piers. We censor our slabs. And then finally our beams. And we're going to measure our deflections using string potentiometers. Fairly common technique. Our load test is going to look like this. 4 increments. There's our string potentiometers. And all the load test areas were all formed, lined for the water. And you just see our setup with our data acquisition unit. So here's the loading. There is the ACI criteria. And you can tell here, very stiff structure, right? Very heavy. Real tiny deflections. And then after 24 hours, just have a little bit of residual as the member starts to crack up a little bit. And then unloaded. Now, this pier here is one that I put in there to show you that sometimes at very small deflections, even the slightest of things, change of weather, whatever, can affect your measuring. And we concluded after looking at all the piers that this is likely instrumentation error. So, if I were using 437, because I didn't satisfy the residual deflection, 437 has the permission for retesting. And that's often what you want to do when you first test one of these structures that are very stiff. When you run it up to its maximum load, you get that initial cracking. When you retest, it will very often come right back, and you won't get that residual. You will satisfy the residual criteria, is what I mean to say. So, monotonic is essentially a proof load, slower to perform, generally easy to perform with some sort of dead load, and the criteria is based on deflections. Cyclic, more of a performance, behavioral test, faster to perform with hydraulics, but either one is permitted by Chapter 6 and 562. And I think that pretty much summarizes the two different case studies I wanted to provide for you that kind of walked you through the use of Chapter 6.
The real question for you, it's probably something that you left out because of, in the interest of time. And the question, for example, number 1, could you have taken advantage of moment redistribution since you are looking at negative moments? And the second part of the question is, when you put the HVAC equipment, I would have guessed that shear was going to be your major problem rather than moment. So if you have addressed this.
No, those are two excellent questions, Tony. The moment redistribution was included in our capacity calculation. We just didn't show it for brevity of the presentation. The shear was accounted for primarily with the truss system. So the way they positioned the HVAC units, the shear was accounted for, but the bending load was still imposed upon the one-way slab.
Another question.
Yeah, you mentioned on the strengthening process that you had to validate that the means and methods you used were not vulnerable to fire and other external loadings. How did you deal with the FRP regarding fire?
There's an equation provided in Chapter 5, Tony. I believe it's 5.5.1, I believe, is that. And if you can satisfy that in the event of the fire that you're not relying on your strengthening to carry the dead load, then you can satisfy that provision. So that is the answer to your question.
Additional questions for Chuck?
A curiosity question. Great presentation, by the way. On the cores and the calculation for the little equation for the cores, it is different from ASTM, and I was just curious about the background about why the committee chose to use a different equation than what's in ASTM.
Great question. Thank you very much for the question. If you know a little bit about the background of ASTM 214, one of the two methods there was developed by Dr. Mike Bartlett. Mike and I worked on Chapter 6 together. The subtle difference in the equation is just that we use the coefficient of variation because it's unitless. So we made it easier for the practitioner, less bookkeeping.